All right, so a standing wave is a special kind of interference where it's interfering with its own reflection. So if we've got a box or a pool or a flute, something that could hold a wave. If we have I'm trying really hard to, there we go. That's not as good as I was trying to draw. We then get a reflection of the wave, which I'm going to draw in a different color. So the wave reflects off Man, I am just not. My art game is not on point today. Please don't judge me.
Too late.
So standing waves are self-interference. Um, so in the standing wave, so in the video we watched, in both say the Rubens tube and that experiment in the pool, you saw portions of the portions of the container that vibrated up and down, and portions which were just always zero. So like in the Rubens tube, we had ones that were flames that were always high, and we had points where there were no flames at all. In the water, we had parts of the water that were always flat, and parts that vibrated up and down. So the idea behind this is actually the same as the idea behind the interference we just did on the last board, right? So if we have a container that's closed on both ends, then the number of half wavelengths that we can stably fit inside the tube is what's constrained. So you will get standing waves, like stable waves, that don't appear to travel if the length of the tube is equal to some integer times a number of half wavelengths. And here, n is just an integer, or a natural number, to be more precise. So you can fit a half wavelength on the in the container. You can fit two half wavelengths in there. You can fit 3 half wavelengths. Do we have any musicians out there? Anybody who plays an instrument? Just mention in the chat if you're musically inclined. Yeah. So we've got quite a number of musicians. I was a cellist by training when I was younger. So in a string, a string instrument has both ends of the string constrained. So at, say, the neck of a string instrument, a violin or a cello or what have you, the string is constrained, and then also at the bridge of the instrument. But in between those two, we can get vibrations. So when we talk about the note that a string plays, we're actually talking about its resonant frequency. So fitting 1/2 a wavelength on the string. But anyone who's been around a string instrument knows that there's a kind of richness to the sound, right? You don't really just hear one note. You also hear a bunch of overtones, right? Because you're also hearing the n equals 2 vibration. So the blue here is the n equals 1 vibration. The pink here is the n equals 2 vibration. You're also going to be hearing the n equals 3 oh man, I can't do this. Let's see. That's close enough. N equals 3. Any wavelength that's on the string which doesn't correspond to one of these resonances will die out very quickly. Usually too quickly for our ear to register. But notes that do correspond to one of these resonances, that's what we hear as the note of the string. So if we're talking about string instruments, this is the neck and the bridge. But it actually works exactly the same for woodwinds. So if you are playing a flute, the flute is open at both ends, which means that the air pressure inside the flute is constrained to be 1 atmosphere on one end and 1 atmosphere on the other end. So any sound waves inside the flute, any acoustic waves, have to be one of these resonant frequencies or they just quickly die out. So all of the notes that you're actually hearing from a flute are resonances, where instead of like on a string instrument, you have an actual physical string that's wiggling up and down. In a flute, what you have are air pressures, just like in the Rubens tube video that we watched at the beginning. So these are actually covered in a fair amount of depth in the book. This is 17.5, so sound interference and resonance. So I'm not going to go too much more into this because it's covered pretty well in the book. Also, what I'm not going to cover too much today is there are formulas for what the wave speed on a string is, for example. And I'm not gonna cover that today. We've got too much to talk about. And as much does piano follow similar rules to guitar and other strings? Absolutely, because a piano string is constrained at both ends. There are instruments that don't quite follow this. So, for example, an organ has pipes that are open at one end and closed at the other, which means that the air pressure at the open end of the tube, so the pressure wave inside the pipe, has to get to a pressure of 1 atmosphere on the open end of the pipe, but it can be anything at all on the other end of the pipe. So for strings and double open instruments, we end up fitting a number of half wavelengths inside on the string or inside the instrument. For an organ, you end up fitting a number of quarter wavelengths inside the pipe. So that's why organs can have such extremely rich overtone sounds compared to even strings or woodwinds. What I would like to cover is Doppler effects, decibels, and ultrasound. I know we are starting to run out of time, so I'm going to move through these as quickly as I may. Let's start with the Doppler effect. So once again, Wikipedia has a just fantastic animation that I want to share with you all. So we're going to start there. All right. Oh, I guess it would help if I shared my Chrome. All right, so this is the idea behind the Doppler effect. If you have a source that is not moving, then when it makes a sound, it's emitting those sound waves in all directions, right? The thing that I'm always thinking about when I think about Doppler is ambulances, right? Because we have all had that experience of an ambulance driving up behind us, and the pitch of the ambulance getting higher and higher as it gets closer, and then it gets lower and lower as it goes away from us. So this is an example of why that happens. So stationary, we have waves emitted in all directions, and we actually hear the same frequency as the source emits. Right? So if we are, say, sitting next to a fire truck, that's what we would hear. Wow, that is really bad, and it's all right. All right, in the middle, this is what the waves look like when the ambulance is approaching us. So the ambulance is still emitting waves that at the same frequency in all directions. However, it's also moving, and the speed of the wave is fixed by the medium it's traveling in, namely the air, whether or not the source is moving or not. So we get this kind of pile up of waves in the forward direction because they can't get away from each other as fast as waves behind the source can. In the extreme case, if we're actually breaking the sound barrier, our source is moving faster than the waves can. And so there is no sound transmitted at all in front of the object. The only sound you can hear is behind the object. Okay. So this is one of the sections where I don't actually enjoy the way your book covers the Doppler effect too much. I actually like the way that Wikipedia gets it nice and compact instead. So the Doppler effect tells us what frequency we will hear compared to what frequency is emitted for either a moving source or a moving observer, right? They end up being the same. So whether the ambulance is moving toward us or we are moving toward it, we'll observe the same effect, although really, you should pull over and let the ambulance move toward you. That's the law.
So I have a small question. It may not be related to what you just said.
Sure.
So when they speak of waves, do they talk about the transverse waves, or do they talk about longitudinal waves?
for this, right, this is an acoustic phenomena. So it's all longitudinal waves.
And is there a separate one for transverse waves?
No, it actually behaves the same. So as we'll cover this later in the semester when we talk about the Doppler effect for light, but it follows exactly the same form and for exactly the same reasons.
Gotcha. Because when you were showing the animation of the Doppler effect in motion, let's say breaking the sound barrier, because what light is also wave energy, can that principle be the same?
Yes. Um, so it's actually one of the strongest arguments, like the not the strongest, but like it's an easily digestible argument for why nothing can go faster than the speed of light. So if an object was going faster than the speed of light, then information transmitted by light would not be able to catch up with it. But all things that are made out of matter are held together by electric bonds, by electrostatic bonds. And the thing that tells an atom that it's part of a bond is actually light. Like the exchange of photons is what tells two particles that they are bonded. So if you go faster than light, light can't catch up to tell things that they are bonded, so they just disintegrate.
And so this is kind of like a Star Trek sort of like homage, but so pretty much unless, like, say, we isolate that so the matter doesn't get like disintegrated, then that would be like warp speed and stuff, right?
Yeah, I mean we're in the realm of sci-fi now, but as
Yeah,
far as we know, uh, it is not possible to travel faster than light because matter would cease existing as matter at those velocities.
understood. So that's like a upper course of physics or something to go over.
Yes.
Got it. Thank you.
Yep. All right, so I want to work through one Doppler shift problem. There are definitely more in the book, and I definitely recommend that you do a few of these. Let's say that you have an ambulance whose velocity is equal to, I don't know, what speed does a ambulance go at? Maybe 30 meters a second? And the frequency of the sound that it is making, we'll just stick with 440 hertz. It's right in the middle of human hearing. So if we are in front of an ambulance, here's the ambulance, and it's emitting these waves. Here is us over here.
I have a question really quick.
Yeah.
You're saying that the velocity of the ambulance is 30 meters per second?
Correct.
Okay.
The velocity, the speed of sound in air, right? So you see we're going to start using V's more, like too many V's. So it's traditional when we're talking about Doppler to let C be the acoustic speed in a medium. So for air, this is going to be 343 meters a second. Does that make sense?
Could you repeat that one more time? Sorry, I just want to make sure that I get it.
Yeah, so V here is going to be the velocity of the source, right? The velocity of the observer will be VO. Right, so subscript O for observer, subscript S for source, and then c is going to be just the speed of sound.
So that would make c a constant.
Yep. For our purposes, we're going to treat it as a constant. If you wanted to be really fancy about it, the speed of sound actually depends on temperature and humidity and barometric pressure, but that's a lot. We're gonna drop that for now. Speed of sound in air is just 343 meters a second.
Yeah, that was actually going to be my next question. Will we have those variations? Because in Gen Physics 1, at least, we're told at least that it will change at times, and so always pay attention to what it's telling you.
Yeah, I'm not going to try to trick you that way.
Okay.
That's just way too much.
Quick sidebar. I'm really wishing I had like you for my Gen 1 or Physics 1 class last semester. Holy crap. You're making this actually fun to learn physics.
Well, I will take that as a compliment, sir.
Well, you should, because it's high compliment as I can give right now.
Alright. So we're going to follow the same problem solving procedure as before. We draw a picture. We specify coordinates. And there's a very special set of coordinates that we use for Doppler problems. It's not the only way to do it, but it's the easiest way. So the positive direction is from observer to source. So that is the positive direction. There's no vectors involved in our Doppler problem, so we're going to skip over that. But then we need to pull out our physics. So the physics we have here is the observed frequency is going to be equal to the source frequency times c plus the speed of the receiver divided by c plus the speed of the source. And that's all the physics. So now we just got to plug and chug.
The receiver is in the observer, right? VR.
Oh, that's right. Sorry, I switched subscripts halfway through.
Oh.
Well spotted. There we go.
Talk about trying to trip us up.
All right. So our source frequency is 440 hertz, A above middle C. Our speed in the medium is 343. And the speed of the observer, that is us standing on the sidewalk, is 0. In the denominator, again, speed of the medium is 343. And the speed of the source is 30 meters a second, but note that the source is actually traveling toward us, which in the coordinates of Doppler problems is the negative direction. So we'll have 440 times 343 over 313. All right, so 343 over 313 is bigger than 1. So our observed frequency is going to be bigger than 440, which meshes with our intuition, right? Like, our experience is that when the ambulance is coming toward us, we hear a higher pitch, and when it's going away from us, we hear a lower pitch. So it's nice that, a little sanity check, this does actually match what we expect.
In terms of units, are you a big person about if you don't see units, it's completely like incorrect?
No. As long as you have, like, so up here when I stated the things that we were plugging into it, I gave the units on each of them. And at the very end, I will give the units on the final answer. I consider that to be more than enough. I don't need the units on your intermediate steps. But units can be a useful check for you, right? Because if you don't get the unit out that you expect, then you know something went wrong with the algebra. So you don't have to show it to me, but it could be useful for you.
Okay, understood.
Okay, so we're going to hear something like 482 hertz. Does anyone know what musical note that is? It's a G? Okay. Oh. I believed you. That's going to be D above, D above middle C. Or no, D2, right? So the second D above middle C. All right. So that's Doppler shifts. Anyone have any questions or comments here?
I'll just say that's way easier than the first time I did it.
Yeah, I have yet to see a textbook which does a good and simple job of explaining the Doppler effect. I just direct my students to Wikipedia for this one. Okay.
I have a question really quick.
Yeah.
Oh wait, I think I just figured it out. The reason why we're solving for the frequency at the person is because it's stationary, correct?
Well,
That's why it's frequency of naught, and the equation is solving for the frequency at the ambulance because it's moving.
so you're almost there. So F0, it's not F0, but FO, right? So the frequency that our observer hears, in this case, us, right? So it's what frequency will we hear, and then Fs is the frequency at the source, right? So
Yeah.
if we were running toward the ambulance, like that would change the frequency a little bit.
Yeah, because we'd be the ones moving and the ambulance would be sitting still.
Yeah, or we could both be moving. That's also perfectly fine.
Okay, then the frequency would become even higher.
Uh-huh.
Okay, yeah, that makes sense. Thank you.
Welcome.
So I have a question. For
Wait,
example,
wouldn't it be lower if you were running towards the ambulance?
yeah, that's my
Yep.
If you're running
No,
toward-
you're right. No, never mind. Sorry, no, if you were going towards it, it would be.
Yeah, so because if you're running toward it, you're running in the positive direction, so the numerator gets bigger.
Yeah. Okay, sorry.
So if you're running towards the ambulance, it would be the top part would be c plus, let's say, 0.5 meters a second.
Yeah, it'd be c plus whatever the speed you're running at is.
Don't chase ambulances. It'll make you deaf.
I mean, that's one of many reasons not to chase ambulances. All right. Any more comments on this page? So we're gonna switch over to hearing.
Closest note I can find in that hertz scale is B4.
For 482?
Yeah, because B4 it says is 484.9.
Oh, you're right. I was looking at wavelength. You're right. That's B4. Okay. All right, so let's talk about hearing. The human body is a weird, weird thing. I don't think I need to tell any of you that. One of the weird things about it is that our senses are actually really bad at detecting absolute changes in stimuli. So, part of this is because of just the huge range of stimuli that we're able to process. So, this is true of temperature, like our sense of heat or hot or cold, our sense of hearing, our vision. For all of these, all of our senses operate on a logarithmic scale, which means that for something to seem twice as much to you, it actually has to be 10 times as much. So for hearing, if a sound seems twice as loud, there's actually 10 times as much energy in that sound. Same goes for the intensity of light that enters your eye. If it seems twice as bright, there's actually 10 times as many photons entering your eye. Same thing for heat, right? If it seems twice as hot, it's actually 10 times. So yeah, it's one of the great oddities of human biology. Fortunately, mathematically, we have a way to deal with this, and the way we deal with this is logarithms. Now, show of hands in the chat if you are 100% comfortable using logarithms.
Kinda.
Yeah, so that's nobody then. That's fair. That's fine.
There was one person who said yes.
Really?
Jessica.
That person is lying.
She said yes. I will tell you, I taught logarithms to an 8-year-old, like, super genius once. Like the kid, he's now 13. No, yeah, he's now 13 and starting college. He got a 1350 on his ACT when he was 11. So when he was 8, I taught him logarithms, and literally in 5 minutes, he was way ahead of me. Like, he was doing fractional logarithms, negative. Like, it was the craziest thing I've ever seen. He just, yeah. Anyway, but the rest of us are not like that. So.
Okay. So I put a link in the chat. Watch this later. It's my favorite YouTube video about logarithms, which I know seems really specific, but it's a great video, and logarithms are great, and you should all watch it later.
Noted.
But for now, I'm going to go over just a little bit about logarithms. So first of all, I like to think of mathematical operations as answering a question. So like when you are doing addition, if that addition answers the question, like how big would the group be if you took these two groups and you smushed them together, right? Well, the answer to that, if you had a group of 5 and a group of 7, if you put them together, you'd have a group of 12. Right, that's the question that addition asks and answers. Multiplication, answers the question. Well, what if you had 6 groups and each of them was had 5 things in it, right? Well, that would be 30. So that's the question that multiplication asks. Exponentiation asks the question, if you did multiplication by 3 4 times, how much bigger would it get, right? So that's the same as 3 times 3 times 3 times 3, right? So it's a lot. Roots and logarithms ask kind of the reverse question. So if we're asking for the square root of 81, what we're asking is what number, if you multiplied it by itself, would give you 81. I don't know why I wrote cubed. I definitely meant squared. So if x is the square root of 81, then x squared is equal to 81. And that's the kind of back and forth between roots and logarithms. Or sorry, roots and exponents. If we had log base 3 of 27, okay, so with roots, our variable, like our x, went in the base, right? And then the kind of root we were taking goes in the exponent. But with logs, it's the other way around, right? This 3 becomes our base, and the x is a variable. So log base 3 of 27 asks 3 times itself how many times gives you 27. And here Jessica is very correct in saying that this is 3. So 3 to the third is 27. So in practice, you could choose, or in principle, you could choose any base you like for logarithms. In practice, there are exactly 2 that we care about. If we just write log with nothing for the base, we mean log base 10. Right? So we're asking 10 to what power gives you x? The other base that we care about is log base e. And we usually write that as just ln, natural log. And that asks the question, e to what power is equal to x? So these are the 2 that we care about. For our purposes here, we're actually just going to use base 10. Right? And that's because of this relationship to human biology. Right? That 10 times as loud, or 10 times as much energy seems twice as loud. That means that the log of the energy is going to be proportional to our human experience of the sound. So we're just going to go ahead and use log base 10. There are a few things about logs that I want to remind you. Logs have some very nice properties. So the log, the sum of 2 logs is the same as the log of the product of those 2 things. Right. Similarly, if we have log of A minus log of B, that's the same as log of A divided by B. If we have log of a to the b power, that is the same as b times the log of a. So these are the three main properties of logs that we're going to make use of. But all of you remembered that already, right? Nobody needed this refresher? The last tool we need before we talk about human hearing is the idea of intensity. So everyone knows what energy is, right? What's energy?
Measure of capacity to do work.
I can tell you got that out of your chemistry book.
I did a lot of chemistry work, but not chemistry book.
That's a perfectly fine definition for energy for our purposes. Energy is the capacity to do work. So there's a related quantity called power. Power is the rate at which you deliver energy. Energy is measured in units of joules. Power is measured in in units of watts. So a watt is 1 joule of energy delivered per second. The second related quantity we need is called intensity. And that measures talks about how spread out our power is. And there's no special unit for that. We just measure it in watts per square meter. For reference, on a sunny day in Las Vegas, the sun is pounding down about 900 watts per square meter of intensity. So it's a lot. Comments or questions on this page? Okay. Now we're ready to actually address human hearing. We have a scale called the decibel scale. And our decibel scale is defined as follows. In terms of the log base 10 of the intensity of a sound in reference to some reference intensity. And usually this is the threshold of human hearing. Okay. The threshold of hearing is about 1 picowatt per square meter. How many powers of 10 is pico?
10 to the negative 12.
That's right. Okay. So let's do let's do one problem from here. Let's say that you've got some nice headphones. They're not active noise canceling, but they've got some, they're like hearing protection. So if you're doing, using a jackhammer, or you're down at the range, you put on some hearing protection. And let's say that your hearing protection is rated for 25 decibels. That means that sounds will that you'll hear things 25 decibels quieter in your hearing protection than you would without hearing protection. So my question is, what percentage of sound energy do they absorb?
I'm assuming by you asking the question that it's not linear then. It doesn't just reduce by 25 somehow.
Yeah, no, it's not linear. It's logarithmic.
All right, you're gonna have to show us.
Yep.
Or at least me. I don't know, maybe other people.
So we're gonna say beta 0. Let me change colors. That's too much black. Beta 0 would be no hearing protection. And beta 1 is going to be with hearing protection. Okay. And the rating on the hearing protection tells us what this difference is. This difference is going to be 25. But we can also write down what beta 0 and beta 1 should be based on our definition of the decibel scale here. So it's also going to be 10 log of, oh, you know what? I shouldn't use 0 and 1 because I'm already using a subscript 0 in here. I'm going to call this A and B. Nope, because B looks like beta.
Well, since the subscript 0 just represents initial, and I and B represent two different things, wouldn't the subscript 0 be okay in this instance?
Well, in a minute, but you'll see in a moment that I'm going to end up with two different I zeros, and that's going to be confusing.
Oh, okay.
So you know what? I'm going to have to just say this is lowercase a, lowercase b. So the decibel rating without hearing protection, that's going to be 10 log of whatever the sound intensity is in reference to the threshold of hearing. And for B, it's going to be 10 log whatever the intensity is with hearing protection in reference to the threshold of hearing. So I'm going to do two things algebraically from this line to the next. I'm going to factor out the 10. Actually, let me do this one step at a time. So we're going to factor out the 10. And then we're going to use properties of logs to smush this difference into a single logarithm. Right? So on the last page, we remembered that the difference of two logs is actually the log of the quotient of those two arguments. And then our threshold value will cancel out. I'm going to move up to the top of the screen here. And I'm going to divide off that 10 on both sides. So we'll have 2.5 equals the log of the intensities without and with hearing protection. Oh, and you know what? I forgot a very important thing. Wait, no I didn't. Never mind. We're good. Okay. So we don't know what IA or IB is, but I would like a comparison of, I would like to know what the ratio is of IA to IB, not the log of the ratio. So to undo the logarithm, you have to use both sides of the equation as an exponent of 10. So we have 10 to the 2.5.
Real quick, you got the 2.5 from dividing the 10 next to the log from both sides?
Correct.
Okay, thank you.
But here, 10 to the power of log, they will cancel out. And so we just get 10 to the 2.5 equals IA over IB. And 10 to the 2.5 is something we can plug into our calculators. So without the hearing protection, the sound has 316 times more energy than with it. Another way of saying that is that the intensity with your hearing protection is only 0.003 times the intensity with no hearing protection. So you're getting less than 0.5% of the energy making it through to your ear, which could be real important if you want to keep your hearing. Antonio asks, can you go over how you got the 10.5 again? Yeah, it's 25 over 10. So the 25 came from the rating on your hearing protection, and the 10 came from the definition of our decibel scale. All right, questions or comments here? That's right. If you have 25 decibel hearing protection, it absorbs 99.997% of the sound energy.
This might go a little bit off the scope, but like with those variable type headphones that use like static, do those work with the same like thing in mind, or is it slightly different in another sense?
They combine it. So if you have really fancy noise canceling headphones, and I mean like we're talking like the $300 to $500 range, they will have some hearing protection, like they will just block something, some amount of the sound straight up, but then they will also use destructive interference to completely cancel out the loudest sounds. Oh, you know what? Isaiah's right. The 0.003 is 0.3%, not 0.003%. So yeah, it'll block 99.7% of the sound energy. 25 decibel hearing protection earmuffs can be had for $12. So if you are doing anything loud, I strongly recommend you get a pair. So you can see that there's a huge difference between the passive noise canceling, which is just hearing protection, which you can get for $12, and the active canceling that you get from the fancy headphones, which are going to be $300.
I'm sorry, can you go over the sequence where you went from 316 equals IA over IB, and then how you got 0.003?
Oh yeah. I just multiplied both sides of the equation here by IB to get IB onto the left-hand side, and then I divided both sides by 316. And 1 over 316 is about 0.003.
Oh, okay, gotcha. Thank you.
All right, so unfortunately I did not have time to cover ultrasound today. Ultrasound is, very useful for you all in your pre-medical fields, but it's an application of reflection and Doppler effect. So I will leave that to be read on your own, and we can have a little discussion about it next week if needed. But other than that, that's everything from chapter 16 and 17 that I intend for you to be responsible for.
So I'm just making sure with the schedule that you have on the syllabus, that is like tentative to what we have to do each week. Because for this week, I was kind of confused because when I read the email, it said like chapter 16, and then when I read the schedule, it said 16 and 17. So I was kind of confused.
Yeah, I didn't expect you to read 2 chapters the first week before we'd even met. That seemed like too much. Jessica, yeah, go over ultrasound over the weekend. So when you're preparing for next week and reading for next week, make 17.7 part of what you read, and we will cover ultrasound very briefly next week at the beginning of class, or right after our quiz. So that means that the quiz will not be on ultrasound, but it could be anything from chapter 16 and then up to 17.6.
Does anyone want me to enter into the chat the group me link? I'm going to take your silence as a yes.
I just have one more question. So to get the actual percent of sound energy, you just multiplied the 0.003 by like 100% and then subtracted it from 100%?
Yeah, that's right.
Gotcha.
Antonio, and is any including the sections I didn't explicitly talk about? Yes. So I'm going to put up a survey on Web Campus asking, because I haven't set whether I'm going to have my office hours on Monday, Tuesday, or Thursday afternoon. So I'm going to put up a survey and ask what most people can make if they indeed plan to make use of it. But I will also, in general, be available for half an hour after class to answer questions that you might have had on work that you encountered during the week that didn't get adequately explained during lecture.